Good morning, everybody. Welcome to Chapter 8, Rotational Motion. And I guess this is how things are going to go for the next little while. And we will do the best we can. So let me start at the beginning of this chapter, kind of giving you at least two things that I really want you to remember as we go through this. You have two different ways to measure a revolution of a circle and a fraction of that revolution. So a fraction of one complete turn of a circle in radians is 1 over 2 pi. And in degrees, it's 1 over 360. And that makes sense because one complete revolution, like one complete turn of a circle, is 2 pi radians, or as you're more familiar with, 360 degrees. Does that make sense so far? Good. Let's get into some other stuff. The second thing I want you to remember is when calculating circular motion, counterclockwise is positive and clockwise is negative. That probably goes against the way you're used to thinking about things. So the way a clock normally moves, we would consider that in a negative direction. And then backwards, counterclockwise, is positive. Yes, I know, physics never makes things easy. So if you guys will turn in your books to page 207, yes, get your book, and yes, page 207, and please get your calculators. You want me to wait? I'm not waiting. So pause this if you need to get that. Again, it's page 207. All right, let's look at number 1. So number 1, we have what is the angular displacement of each of the following hands on a clock in 1 hour? And you'll need to state your answer in 3 significant digits. So let's look at part A, the second hand of a clock. Well, as you can see, I wrote it out exactly how I talk. Well, how many times does the second hand make a complete revolution in 1 hour? So we know that one revolution of the second hand equals 1 minute. So every time that little thing goes around, 1 minute is gone. How many times does it have to do that in an hour? 60? You've got it. So every time the second hand goes around, that's 1 minute. But since we are looking for the movement of the second hand in 1 hour, we have to use the calculation of 60 revolutions. So once we know that, what is our formula for angular displacement in radians? Well, I'm glad you asked. So the theta of the angle that we're trying to get is the number of revolutions times 2 pi, because remember, 2 pi is a whole revolution. And please remember, because the clock is going clockwise, like a normal clock, 2 pi is negative, because clockwise in physics right now is negative. So how do we solve this? We're going to use this formula, that theta is equal to the number of revolutions. Well, the second hand goes around 60 times. So 60 revs times negative 2 pi radians. So this is equal to negative 120 radians. And you can just drop the revolutions and replace that with radians. And then if you go ahead and calculate that, if you calculate the 120 times pi, you'll get the negative 377 radians. Does that make sense? Just keep referring to this formula, and also remember that this is going to be negative because we're going clockwise. Well, let's look at part B together, okay? All right, so part B wants us to look at the minute hand. So how many times does the minute hand make a complete revolution in an hour? How many minutes are in an hour? There are 60, right? But the minute hand isn't just like the second hand. It doesn't go around 60 times. it only goes around one whole revolution, and then that makes up our 60 minutes. So it only goes around once because the minute hand moves only a little tiny bit for each minute that passes. So to get a whole hour in there, it moves all the way around one time, and that marks our 1 hour. This is going to be easy because now our formula is going to be, well, your theta, your angular displacement, is going to be 1 revolution times negative pi. That's simple. We can all do that. So your answer is going to be negative 2 pi, or if you go ahead and calculate it, it's going to be negative 6.2 radians. Okay? And if you hear snoring in the background, that's my mastiff. Even physics bores him. So let's move on to the last part of this problem. So finally, part C. How far does the hour hand move in 1 hour? Well, clearly it only moves 1/12 of an entire revolution because on a regular clock, there are 12 hours that make up 1 revolution with the hour hand. So let's put that into our equation. So our theta is going to be equal to 1/12 times negative 2 pi radians. Again, the 1/12 is revolutions, but when we use radians, we can drop the revolution from the equation. So if we just put that right in, you're going to see that we get negative 2 pi over 12. Well, let's reduce that because we can. So this will take us to negative pi over 6 radians. And again, if you calculate that, you will get negative 0.523 radians. And why do we go out that far? Because the book asked us to. I'm going to stop us for that right here, and I will work on putting up the second problem for you in just a little bit. Thank you.